All right, so we were talking anomaly detection and roadmap. We're going to start with continuous data and detecting anomalies within continuous data. So let's jump right in. I love this quote from Hawkins in 1980. Observation which deviates so much from other observations as to arouse suspicion it was generated by a different mechanism. It's an interesting definition of an outlier. It's just so dang different than everything else that maybe it was generated in a different way. So mentioning that we have some reminders in this lesson rather than brand new stuff. The first reminder is very critical. Always visualize your data. It just, unless you have so many data points that it can't fit into memory, and even then you can take a sample of a couple million, put them in a pandas data frame and visualize. There is no excuse for failing to visualize your data. Really, there's just simply no excuse because it's so dang easy. We are visual critters, so we think very visually. So a couple of tools that we can use very regularly to visualize our data: box plots. Box plots are bread and butter visualizations, and scatter plots as well. The nice part about scatter plots is that you see a data point for each, you see a point on the chart for a point in the data set. My coffee tasted so good, I decided to share a bunch with my table here. So give me just a sec. It's better than sharing it with my lap. So I'll take the spilled coffee on the table though. Another visual that is really, really powerful and just it's like keeping a pocket knife with you when you're going camping is a histogram. Visualizing the distribution of either continuous or discrete values, just getting those value counts goes such a long way towards understanding things. And just .hist on a pandas data frame will get you rocking and rolling. Remember Anscombe's quartet. And if you don't remember Anscombe's quartet, we will revisit this. We've got some code in the curriculum so you can generate Anscombe's quartet. We have 4 different data sets inside of a data set. And really a bunch of their values were very similar, right? Very similar means, very similar standard deviations, off by just tiny rounding errors. Pretty similar interquartile range and Q1, Q2, Q3, Q4. And if we were to judge Anscombe's quartet by the descriptive statistics, you might come to the conclusion, incorrectly, you might come to the conclusion that all 4 of these data sets are pretty similar. But when you graph and chart Anscombe's quartet, we see 4 totally different stories. And in 2 of those stories, we see some outliers, don't we? So the lesson of Anscombe's quartet is don't be fooled by descriptive statistics. Chart your stuff. Always visualize your data. Data set 1, we have a it's not a super tight relationship, but there's totally a relationship there. Data set 2, totally a relationship, and it's a parabola, so that's a polynomial. Data set 3 and 4 are, it seems like most of the data is suggesting we have a straight line relationship. With an outlier. So always visualize your stuff. Scatter plots are your friend, and also box plots are your friend as well. And histograms, like all 3 of those, give you a real good visual idea of where your outliers are. So let's keep going. There is something, you may have heard of this one called the empirical rule, or also known as the 3 sigma rule. This one, it comes up, at least where I've heard this in my work and research more commonly, is in finance and predicting probabilistic outcomes and prices, or if options expire worthless, or if options expire in the money, that kind of stuff. But more simply, the 3 sigma rule it is built on the assumption of a normal-ish distribution, maybe not perfectly normal distribution of a variable, but if we have a normal enough, not too much skew, not like a beta distribution or an exponential distribution, what we end up getting is that almost 70% of our observations are within one standard deviation of the mean. So that's good to know. If your data is relatively normally distributed, plus or minus one standard deviation, you've got almost you've got just a bit more than 2/3 of your data. Two standard deviations, excuse me, contain 95% of our observations, and that's if we're normally distributed. Now, whether if your standard deviation value is very large or very small, this is still going to hold for normal distributions, which is it's almost counterintuitive. But that area under the bell curve covers quite a bit. 99.7% of observations are within three standard deviations of the mean. So what can we do with this 3 sigma rule? Well, one approach would be almost as a kind of a quick test for normality. We might say, hey, if we know the standard deviation of a given data set, and then we calculate the percentage of values that are within that, it's reasonable that we might be able to kind of back a napkin check if that's normally distributed. However, this specific rule, this empirical rule here, is very commonly over applied to data that's not normally distributed. The financial industry is kind of a big culprit here, especially assumptions like efficient markets hypothesis is built on an assumption of normality. We won't go into efficient markets hypothesis too much. It's just, it's assuming that all information about an equity is priced into it already. So if you believe efficient markets hypothesis, you don't have to read the news on your stock because the price of whatever bad news or good news is already priced into the asset. But this empirical rule can be oversimplified, right? I've got a link here to making a common mistake, which is if we drop everything outside of 2 standard deviations. This is kind of this isn't really a rule, but it's an unfortunate practice where folks just drop things that are 2 standard deviations away from the mean and higher. And you end up destroying a bunch of data. And I love this, even if your supervisor tells you to. Give this some time. It's a 5-minute video. It's worth your time. I'm not going to play it for you right now. We'll just keep on rocking and rolling. But some really weird stuff happens when we get pretty far away, when we get multiple standard deviations away from the mean, right? So let's say we have an event that happens daily, right? So if we're doing something daily, if a value is within half of a standard deviation, plus or minus, so that if the normal behavior is for something to happen daily, then plus or minus half a standard deviation that observation would happen for 5 times a week. If we move to 1 standard deviation, that observation, that outlier would happen twice a week. And as we get farther and farther away for where the thing we're measuring every single day, this is the extreme observations of like 2 sigma plus or minus 2 standard deviations away. We might expect that to happen at least once every 3 weeks. And as we get farther and farther, again, this is assuming normality, as we get more and more standard deviations away from the mean of where the normal thing is happening one time a day, if we're 6 standard deviations away from the mean on an observation, that's every 1.38 million years. So it might be a little challenging to wrap your head around what's going on here. The setup is if we're observing something normal once a day, how often would something abnormal happen if that abnormal thing is defined by how far away it is as a standard deviation. And so this chart, this empirical rule, generates, at least in my personal opinion, I'll inject some personal opinion in here. It injects some overconfidence into a lot of people's models, especially financial ones. Like, if somebody came to you and said in 2006, I don't know if y'all remember 2007, 2008, 2009 very clearly or not in the financial world, but if somebody came to you in 2006 and said, hey, I got this model, and the only time the model is ever going to lose is if we are 6 standard deviations away from the mean. And that's only going to happen, let me tell you, Ryan, that's only going to happen every 3.8 million years. Well, guess what happened in 2007, 2008? We had stock price movements that were 17 standard deviations away from the mean. So the punchline is these systems, the underlying system of finance was, you know, and stock prices and all that good stuff was not normally distributed, right? But if you built a model assuming that it was normally distributed, you could be very arrogantly overconfident. And then suddenly reality sets in and you have a 17 standard deviation event in one day. Let's see, in 1987, we had another financial collapse. This was, I think this was called Black Monday. This was associated with the savings and loan crisis. That was a 22 standard deviation movement in the stock prices in one day. And so this tells us that we need to be very careful if we are assuming normality for things like building risk models. So beware, the lesson here is to beware of what are called black swan events. Black swan events, that term is coined by Nassim Taleb, who's a financial trader. In fact, in 1987, that's when he made his never have to do what somebody else tells him again money, because he bet against the markets. But he is also a bit of a philosopher. I think I talked with Lincoln before about Nassim Taleb. And he's built a body of work and research, statistical research and philosophy and epistemology around investigating phenomenally low frequency events, like really low frequency events, like 1 in a million chances, but those that have an exponentially powerful impact. The nomenclature for this came from the understanding at the time in both Eastern and Western cultures, the statement "all swans are white." That was entirely true, whether if you're in the East or in the West, until those colonial types started colonizing Australia, and the Australian Aborigines said, "Yeah, we have swans that are not white. They have black swans, right?" To look a little bit more into that, there's a great book by Taleb called "Fooled by Randomness." That's great for a book club if you're feeling up for it. But the punchline is, even if your data looks normally distributed, remember that those low events in that very, very far away fat tail, where a model might say, hey, it's only going to happen every 2 million years, 1.5 million years. We seem to have a financial crisis, knock on wood, of double-digit standard deviations every couple of decades. So watch out. What does that have to do with you? Well, you can use things like the number of standard deviations away from the mean something is to generate an understanding, at least if it's a normally distributed thing and not something crazy exponential like a stock market. You could use the z-score for identifying outliers. The z-score, that's what the number of sigmas is right here. So if something is 1 standard deviation away from the mean, it has a z-score of 1. Something's 5 standard deviations away, the z-score is 5. This works really well with data that is actually normally distributed, not things that are subject to a power rule or exponentiation or crazy exponential stuff like stock prices. And we've talked about our third little friend here, the interquartile range rule. In case you've forgotten, you have met interquartile range before. Here's the really cool news. It works pretty darn well for non-normally distributed data. This works, in fact, quite well. IQR range rule came out in 1997 from John Tukey, kind of the Elvis Presley of statistics. And we've got the formula in here. The multiplier for IQRs, you could usually set it for 1.5 to filter out mild outliers. And as you increase that multiple K, we filter out more and more extreme outliers and keep more and more of the rest of the data. So in case you've forgotten the IQR range rule formula, we need to determine the third quartile. That's the single value that is the midpoint between the highest value and the median. And then we need to figure out our Q1, which is the midpoint between the lowest value and the median of a data set. Then we pick a multiplier. It doesn't have to be 1.5 or 3, but if you set your multiplier to 0, that's going to destroy a lot of data. And if you set your multiplier at like 5, you're going to have some data that's pretty far away from the mean. Once you get that interquartile range rule, you multiply it by your multiplier, like 1.5. It gives you your upper bound, 1.5 times the interquartile range rule. Add that to Q3, and we have our upper bound fence. And then subtracting that same value from Q1, we have our lower bound fence. This next little chunk of math brings up the idea that we could create a lower inner fence with a 1.5K to find more outliers, and also set a K of 3 to tolerate some of the outliers that are a bit closer to the median, or to the middle, to the mean. And what might be useful is to paint these as horizontal lines, not horizontal, vertical lines on your charts. Rather than just destroying the data, you can visualize and highlight to show where those fences are. So as I mentioned, nothing too crazy, too new. Interquartile range rule, we've used that a couple of times. That is good enough when you don't have something else, and when it's okay to get rid of the outliers. And maybe if you wanted to make a different data set of just those outliers, you could use the interquartile range rule. Using the number of the z-score for an observation. This tells us how many standard deviations away. We could use that as well. And first and foremost, always visualize your stuff. At the very least, box plots, scatter plots, and histograms of variables in question before getting any fancier. All right, so looking at the exercise itself here, we're going to have you set up a new repository for anomaly detection exercises. So everyone's going to set up a brand new repository on GitHub, set that up, clone it down, and then set up either a Python script or a notebook. It's your call, whichever you like more. And you'll define a function that says get upper and lower bounds, and you'll basically build a function called get upper and lower bounds that uses interquartile range rule. We've got a data set in here called lemonade.csv. This data has some weather information, it has temperature, it has rainfall, it has promotional flyers, and it has sales. Go through all of these, use the IQR range rule to identify your outliers. Are they outliers? Should they be outliers? Do they make sense? Should we keep them in the analysis? Should we toss them out of the analysis? So we'll have you work with the interquartile range rule here. We'll also have you use the 2 sigma decision, then use the 3 sigma decision. And that begs the question, do you toss those outliers? Do you keep them? And there's no substitute for getting to know your data. So this is a lemonade stand, or maybe you could see this as a it's a franchise of lemonade stands. But just have a fun time with this exercise. This is a kind of a synthetic data set. But I think you'll have fun going through here and identifying some stuff. Some pretty interesting stories in there.